Welcome to your lesson on transforming trigonometric functions. This is video 2 of 2, so make sure you watch video 1 first if you haven't yet. In the first video, we looked at transforming by reflecting and translating. In this video, we'll move on to dilations. You can continue to take notes on the same notes page that went with video 1. Okay, just to begin where we began before, you should at this point have a very good understanding of the sine graph and cosine graph, and knowing their key attributes such as the amplitude, which is the distance from the central line to the top of a wave or bottom of a wave, and the period, which is the length of time it takes to complete one cycle, or the horizontal distance required to complete one cycle. Alright, so looking at that, let's move ahead to transformation number 3, which is a dilation. To begin, here's a question. What's the difference between the effect that each transformation has on a function? So we have a function f of x, this transformation has occurred, and this one has occurred. What's the difference? Okay, so if you thought back to what you know about transformations, you may remember vertical and horizontal dilations. This one here is a vertical dilation or vertical stretch or compression because the multiplier or the scalar is in front of the entire function. When it's in front of the entire function, it affects the y values. This one, the 2 or the multiplier, is inside the function there with the x. Therefore, its effect is on the x values. Therefore, this is a horizontal dilation. So let's take a look at those in detail. So we'll begin with vertical dilations first. And as we did before in part 1 video, we're going to begin with a parent graph that is a quadratic and recap what effect our transformation has on that graph before moving on to sine and cosine waves. So here we have a parent function x squared. Here it is graphed. Our rule that we're going to apply here is 2 times the function. So the function is x squared. The child function therefore will be 2 times x squared. So there's our resulting function. Again, this 2 multiplies the entire function, and that means the y values. So all y values are multiplied by 2. That means we have a vertical effect because it's affecting the y values. So the resulting function is the orange one here. As you can see with the given point, on the original graph of y equals x squared, we have a 0.11. But now we're multiplying, so all y values become twice what they were. So here we see this x value remains as a 1, but the y coordinate there becomes a 2. So the effect is the y values have been multiplied by 2. And on the graph, what that does is it stretches the graph, makes it twice as tall. Let's look at that in terms of a sine wave. So here is a sine wave. We know it's a sine wave because it begins at 0. So our parent graph is sine x. The rule we're going to apply is the same one, 2 times the function. So the child is going to be y equals 2 times sine x. Now think about this in terms of what this is doing again. So this again is a vertical effect, is stretching y values by 2. So this is an important note here. When we do a dilation of this type on sine and cosine graphs, this affects the amplitude, right? Because this graph will be stretched up and down. So what is the new amplitude? What is the new period? Well, here's the resulting graph. Let's take a look. Here's the original. When in the original graph, the function goes as high as a y value of 1, but now we're multiplying by 2, so now it goes up to y equals 2. And this one here, the y value is 0 here. That one you'll notice remains at 0, right? Because 2 times 0 is 0. Or over here, we had a y value of negative 1. So when you multiply the function by 2, that negative 1 will become a negative 2. So essentially the whole graph has been stretched 2 times up and down, right? So the new amplitude is 2, right? Because that is now the height of the wave from the center line to the top or to the bottom. It has a height of 2 now. And the new period is 360. So it's not new period, it's the same period. Because again, all our dilations here were done vertically, not horizontally. So notice a period is how long it takes to complete the cycle. Let's check that it's still 360. Begin at 0, go up, down, and you get back to 0 here after its full journey at 360. So we've only stretched up and down, not left and right, so the period remains unchanged. Let's see that some graphs like that compared. So here's a regular sine graph. 2 sine x is going to mean stretched to be twice as high, so there's 2 sine x. 3 sine x stretched to be 3 times as high. There it is. So now the amplitude is 3 here, and then we see it also here, -3. And half sine x means it's going to be half its original height. So if the original height has an amplitude of 1, now half sine x has a height of half. Okay, let's do the same thing with a cosine graph. Here's the original cosine graph passing through 0, 1, then 2 cos x, twice as tall, 3 cos x, 3 times as tall, and half cos x, half the height of the original. Great. So with that, we can do a couple more things on here to recap the amplitude and so on. Here's the amplitude of your original sine graph. Then you do 2 sine x. Now the amplitude is 2. Then you do 3 sine x. Now the amplitude is 3. And the period remains 360 for all of those because, again, these multipliers affect the y values. It's a vertical stretch, not a horizontal stretch. So the period remains 360 for everyone. Okay, a couple more recaps. Here's sine and cosine together. You can see again, sine and cosine has exactly the same shape, just they're kind of shifted versions of one another, or translated versions, right? And then here we have 2 sine x, twice as tall, 2 cos x, twice as tall, 3 sine x, 3 cos x, 3 times as tall, and then half sine x is that the amplitude of a half, and half cos x also. All right, so now we're ready to kind of summarize here as well. See if you can fill in the 2 blue blanks. Okay, check your work there. And now how about filling in the 2 green blanks? And check your work there. Okay, and one other one to kind of get at these ideas we've been talking about. Take a look at what it says here and then see if you can determine the amplitude there. All right, in this one, I hope you went back to remembering that we have to have that central line, and the amplitude is not the entire height of the whole wave, because the entire height is 4. We can see that here, top to bottom 4, but the amplitude is half of that, and then half of that is 2. So it's 2. Okay, let's see another couple combined functions here. So here we're going to have the sine graph and then negative sine. Remember, we talked about reflections in the last video, so this is the reflection over the x-axis, all right? Because the negative applies to the whole function, it's flipped down. Here we have 2 sine x, twice as tall, and negative 2 sine x, again, reflection over the x-axis. So there it is, it flipped from here to here. 3 cos x, so now cosine graph, there's the original cosine graph passing through there, and then negative 3 cos x. 3 times as tall, but flipped over the x-axis. And finally, half cos x and negative half cos x flipped over the x-axis again. Okay, so now we've looked at dilations vertically, so let's go to dilations horizontally. Beginning at our quadratic again, here's our parent function, y equals x squared. We're going to apply a rule of f of 2x. So now the 2 is within the function. It's not outside here anymore. It's within. So it's beside the x. It's affecting the x values. So it's going to have a horizontal effect. And now if you remember the rule here, when you have a 2 there, it doesn't mean it gets 2 times wider horizontally. It means it gets half as wide. So remember with this one, we always do 1 over the number we see here. So the resulting graph, first of all, the function, if you put 2x into this function, that x is replaced by 2x, and we have 2x in parentheses squared. And the effect on the graph is the orange one. So again, when we see a 2 there, we don't make it 2 times as wide, we make it half as wide. So the green one's the original. Here's our point 1, 1. Here's another point on the original 2, 4. But now since we have this 2x here, every x value becomes half of what it was. So this x value was 2, now it is 1. But notice the y value is the same, 4 and 4. So again, the x values are made half. So the effect on the graph is to compress it. See how the orange one is a compression of the green one. So it's compressed into half its width. All right, so let's look at that for sine and cosine. So we're going to begin with a cosine graph now. It begins here, so we know it's cosine. So parent graph is cosine x. The rule we're going to apply is the same one we just saw, f of 2x. This 2x then replaces this x. So we have cosine of 2x. And now don't forget the effect of this 2 is that it is making this thing not twice as wide, but half as wide horizontally. So what's the new amplitude and period? Okay, Take a look at that. So now it is important to note when we do this kind of dilation, a horizontal dilation, so if you're changing the graph horizontally, you're affecting the period. Because remember, the period represents how long it takes to complete one cycle. Well, if we're now stretching or compressing this way, it's going to change how long it takes to make that cycle. So for example, if we are looking at this 2 here and every x value becomes half of what it was, here's an x value at 90, so that's going to be at 45. Or this one that is at 180 is going to be at 90. Let's check that one out. So that 180 should become 90. There it is. Or this one that's at 270 should be now at 135. So crossing the axis should be at 135, somewhere here. There it is, 135. So everything became half its width. And the entire cycle began here, went to here, and finished at 360. It's back to its starting place. But now we're making it half of what it was. So now the cycle should take 180. Watch this. There, and now it's back on top at 180. So the amplitude is the same because we haven't stretched this up and down. We have stretched it left and right, however. So now 180 is our new period. Okay, so here's some examples of that. Here's a sine graph. Here's a sine of 2x, right? Everything's been compressed half. Notice that now where one cycle occurred, now 2 cycles occur. Okay, and here's sine 3x. Again, now in the red one, 3 cycles occur in the original 360, and half x. So now if 3 made it 1/3 its width and 2 made it half its width, the half means it's going to become 2 times as wide. Because if you flip that over, make the reciprocal, it's 2. So now that one is 2 times as wide. So the effect of that is widen it 2 times. Okay, same thing with cosine. Here's regular cos. Here's cosine of 2x, 3x, and then half x makes it actually twice as wide. Okay, fill in the blanks for blue. Check your work. Fill in the blanks for green. Check your work. Okay, and now see if you can answer this one. Read that and see what do you think goes in there. It's that. Think about that carefully. And then let's look at it through an example here. What is the period, frequency, and amplitude? Well, here we go. So check that out. Again, this 3 means the amplitude is 3. This 2 means the graph is compressed half its length. That means the new period is 180. And that's what this thing here basically shows, that little formula. That to get this number, we take 360 and we divide by this number, and then we know what the new period is. And then the frequency is 2, amplitude is 3. Frequency represents how many times the cycle occurs in its normal 360 zone. So normally the frequency is 1, but now frequency is this 2 because 2 full cycles occur in that 360. Okay, try this one. Okay, hopefully you got something like this. Check your work there carefully. Let's see how you did. Next one, try this one. Okay, for this one, check your graph. Check the exact values there. These are getting more tricky. Hope you're thinking about it and figuring them out. With this one, maybe I can recap a couple things. The amplitude is 3 times because this represents the height. This half here tells us that the graph is not going to be half its width, but twice its width. So now the frequency, only half the wave occurs in the original 360, and the period is 720 because it takes twice as long to complete its full cycle. Instead of 360, it's 720. Okay, try this one out. So you have to write an equation. Looking at that graph, what's the equation? There are different answers, but one possible answer is something like that. That's one answer. You could have used sine as well. Take a look at the details there. And try this one, make an equation for that as well. Here we go, looking at the amplitude, looking at a full period. Period is 120 now, frequency is 3, therefore that's one possible function. There's another possible function. Either one of these reflections would have worked for this one. Okay, those last few I have to say are quite challenging considering we've gone pretty quickly through these transformations, but I hope you tried and understood some of the key ideas. These are tricky, but they get you ready for your work in DP for sure. Great work, everybody. See you next time.